So welcome back to Quantitative Chemistry, and this video is going to take you through reacting mass calculations. So that's 1.7.5 on the specification. So we're going to be calculating reacting masses of reactants or products given a balanced simple equation and using moles and simple ratio. We're not going to cover the examples where there's a limiting reactant in this video. We'll do that in a separate video. So I want to start by doing a quick recap of what we've covered so far. So we've looked at what a mole is, and a mole is simply an amount of a substance. Specifically, it's 6.02 times 10 to the 23 particles of a substance. We also looked at some important equations. We looked at an equation triangle, but the two key equations from that triangle is for working out the number of moles, which we represent by the letter N. So N, the number of moles, is equal to the mass of a substance divided by its RFM. So N, number of moles, equals mass over RFM. And then if we were asked to calculate the mass of a substance, we can rearrange that equation to get mass equals N times by RFM. So mass is the number of moles multiplied by the RFM. And we need to remember that when we're using mass in these equations, that the mass is always needs to be used in grams, or if we use the mass equals N times RFM equation, that gives us our mass value in grams. And we can convert it to kilograms or tons if we wish, but to put it in these equations, it must be in grams. So those equations are really important. They're going to be used in all our calculations in this video, to make sure you know those really, really well and go back and practice them if you feel you need to. Other than that, we're going to move on now to reacting mass calculations on page 16. So starting on page 16, we're going to have a look at reacting mass calculations. First of all, we're going to have a think about why we can do these calculations. This topic is called quantitative chemistry, and quantitatively simply means measuring and calculating quantities. And you'll be familiar with our balancing of equations, that we must balance a symbol equation because there are no atoms gained or lost in a reaction. So think back to unit 1.5 when we were writing balanced symbol equations, when we were just balancing them. What we said at the time was we must make sure that there's the same number of atoms on the left hand side of the equation than there is on the right hand side of the equation. Now don't worry, I'm not going to ask you to write any balanced symbol equations in this part of the topic, but what it is important that you know is that the balancing numbers are there essentially so that we can read an equation quantitatively. So what do I mean by that? Well, let's look at an example of a balanced symbol equation. So here we've got magnesium reacting with oxygen to give magnesium oxide. Essentially, this is the equation for the reaction of burning magnesium. You don't need to understand the chemistry of what's going on here, but we want to read it quantitatively. So you'll see I've got my balancing numbers here. So there's a 2 in front of my magnesium. There's no number in front of my oxygen, so essentially that's just 1. Okay, and there's a 2 in front of the magnesium oxide, my product. And these balancing numbers are essentially there to make sure that I have the same number of magnesium and oxygen atoms on the left hand side of the equation as the right hand side of the equations, because as we said, no atoms are gained or lost in a reaction. But those balancing numbers can also be used to read this equation quantitatively. So follow along with me. This equation can be read as 2 moles of magnesium can be reacted with 1 mole of oxygen to form 2 moles of magnesium oxide. These balancing numbers actually give me the ratio of the quantities that I need to mix my reactants in and the ratio of the quantity of the product that I form. So if I was to mix 2 moles of magnesium with 1 mole of oxygen, in theory, I should get 2 moles of magnesium oxide. And what this means is that when I have a number of moles of a reactant or a product, I can actually know the number of moles of all of the other reactants and products in an equation, and that's what we're going to do in our reacting mass calculations. So let's fill in your notes here. Essentially, this is just a ratio. So you could swap this for 4 moles of magnesium would react with 2 moles of oxygen to give 4 moles of magnesium oxide. It doesn't matter the amount of moles, but it just matters that the ratios are right. But let's just stick with 2 moles of magnesium because that makes it a little bit easier. So this equation shows that when magnesium oxide is completely burnt in air, if we were to have 2 moles of magnesium, it would react with 1 mole of oxygen. We can see that by the balancing number ratio. It's 2 to 1 from magnesium to oxygen. And that would give us 2 moles of magnesium oxide. What we want to say from this part of your notes is that we can read an equation, a balance symbol equation, quantitatively, but it's quantitatively in terms of the number of moles. So if I had a mass of magnesium, if I was to be given a particular mass of magnesium that I was reacting, I could work out the theoretical mass of magnesium oxide that would be formed. But I can't just bring the mass across my equation. I've got to bring the number of moles. And that's where our reacting mass calculations come in. Now these can seem a little bit complicated to start off with, but hopefully once you get the practice, you'll see that they're the same each and every time. And with plenty of practice, I think you will find these okay. So what we are doing in these calculations is that we're calculating the number of moles of a reactant, and that allows us to work out the number of moles of the other reactant that are needed for the reaction to proceed. But what we can also do is we can calculate the number of moles of product that can potentially be formed, although we don't always see a 100% conversion into products, what we would talk about 100% yield, but we'll see that later on. But in these calculations, we're assuming that all of our reactants are converted into products. So just like anything, it's a step-by-step procedure that you need to follow very carefully. I'm going to underline some of these steps in different colours, and then I'm going to translate that into our worked example. So I'd encourage you to do the same. Again, this method will seem a little bit abstract at this stage, but we're going to put it into practice in our examples in just a second. So first of all, you will be given information that you know. You'll be given the mass of a reactant or a product, because you can go both ways in these calculations, which we'll see. And the first thing I'd like you to do is write the information that you know underneath the relevant part of the equation. So if we were to look at the previous example, if you were given the mass of magnesium, I would want you to write the mass of magnesium that you were given underneath magnesium in the equation. So write the mass that you've been given underneath that part of the equation. The next thing I want you to do is to write a question mark underneath what you're trying to work out. So going back to that example above, if you were asked to work out the mass of magnesium oxide formed, I would want you to put a question mark underneath magnesium oxide. Next thing you need to write down under your equation is the RFM of the reactants or products that you will be using underneath the relative part of the equation. So again, looking at example, if you were given the mass of magnesium and asked to work out the mass of magnesium oxide, you would need their RFMs underneath that part of the equation. It just makes our calculations then a little bit easier. And with these types of calculations, you will be given the balance symbol equation, and you will be given the RFM of the reactants or products in general. If you're not given them, you'll need to work them out, but in most past paper examples, you're actually given the RFM values. So as I said, you can't bring mass values across your equation. You need to convert them into moles first of all, because then we can use our balancing number ratio. We can't use our balancing number ratio with masses. We can only use that with the number of moles. So step number 3 is to convert your known mass into the moles of that substance using the equation N equals mass over RFM. And some people ask, where do you start? Well, you start with what you know. And what I mean by that is you start with the reactant or product that you know the mass of, because you will then be able to use this equation. To use this equation, you need a value of mass and you need the RFM. So you need to use the one that you've been given the mass of. So we work out the number of moles of the mass that we've been given. Then what we do is we transfer that number of moles to the substance in question, essentially the thing we're trying to work out. Essentially, we're transferring the number of moles to the question mark that we wrote earlier, the reactant or product that we're trying to work out the mass of. And we're transferring the number of moles. You're given a complicated phrase here that says the stoichiometric ratio. The stoichiometric ratio, that simply means the balancing numbers ratio. So if we went back to our equation up above, you can see that if I was going from magnesium to magnesium oxide, if I was bringing my number of moles over, you can see that my ratio of balancing numbers is 2 to 2, because there's a 2 in front of my magnesium and a 2 in front of my magnesium oxide. And that's essentially the same as saying it's a 1-to-1 ratio. So 2 to 2 is the same as saying 1 to 1. So that complicated phrase, stoichiometric ratio, simply means the ratio of the balancing number of where I'm bringing my moles from to what I am bringing my number of moles to. And then finally, we're converting our moles to mass by using the equation mass equals N times RFM. So once I know the number of moles of, for example, the product formed, then I can convert back to mass by doing mass equals N times RFM. Now again, that might all seem totally complicated and you can't quite picture what that looks like yet, but that's why we're going to do a worked example. So over in the next few pages, we're going to do some worked examples. I'd encourage you to even just watch me do these worked examples first of all, and then go back and write them in, just so that you're properly listening through the steps that I am doing, rather than trying to write and listen at the same time. So perhaps just listen along first of all, and then write them into your notes afterwards. Pause the video and write them in. But you've just got a quick reminder at the top is that when we're doing these calculations, you can only transfer moles from one part of the equation to another. You do not move masses. So that's really important. When I'm using that balancing number ratio, it's important that you're using the number of moles, not the mass, and that's why we have to convert to moles first of all. So let's look at worked example 1 here. And you'll notice in all of these examples, I always work directly underneath the equation. And I would encourage you to do that even in an exam situation as well, to rewrite your equation and to do all your working underneath the equation. It just helps you keep a track of what you've done and where you need to go to. So let's read this question first of all. It says, calculate the mass of magnesium chloride formed from the reaction of 4.8 grams of magnesium with hydrochloric acid. So make sure to read the whole question first of all and make sure you understand, well, what am I being asked to do? But let's now follow the step-by-step guide from page 16. So the first thing I told you to do was to write the information that you've been given underneath the equation. Essentially, write down the mass that you've been given underneath the equation. And I wrote that underlined that step in purple. Okay, so I'm going to write it in purple now. So what mass have I been given? Well, here's the mass that I've been given, 4.8 grams. And what's that the mass of? It's the mass of magnesium. So I have 4.8 grams of magnesium, so I'm going to write that underneath the magnesium part of my equation. And what we need to remember is to check that that mass is in grams, and if it's not in grams, you must convert it. In this case, it is in grams, so we're all good. So that's the first part of step 1. Write the information that you know underneath the equation. The second part of step 1 was to write a question mark underneath what you're trying to work out. And I underlined that part in red. So if I go back to my question, I'm told to calculate the mass of magnesium chloride formed. So that word formed means I know it's going to be a product. I know what I'm being asked to work out is a product, but essentially I just need to find it in my equation. Calculate the mass of magnesium chloride. So you're identifying which formula is that? Well, it's going to be MgCl2. So that's the thing I'm being asked to work out. So I'm going to put a question mark underneath that. That's what I'm trying to work out. Step number 2 then was to write the RFM of the reactants or products that you will be using underneath the equation. Now you can write all the RFMs in because you've been given them all, but I don't actually necessarily need to write them all out. So you can see here I've been given my relative formula masses. So what I am going to need the relative formula mass of are the things I have been given and the things I'm trying to work out. So I'm going to need to use the RFM of magnesium, and I'm going to need to use the RFM of magnesium chloride. Again, you can write the RFM of hydrochloric acid and hydrogen underneath them if you want, but we won't actually be using those. So what's the RFM of magnesium? Well, we can see here it's 24. So the RFM is 24 of magnesium. What's the RFM of magnesium chloride? Well, it's MgCl2. It has an RFM of 95. So in general, you will be given these RFM values. If you're not, then you will need to work them out, but generally you'll be given them in an exam, so please do look out for them rather than calculating them yourself and then making a mistake. So that's step number 1 and step number 2. Step number 3 then says convert your known mass into moles of that substance using the equation N equals mass over RFM. And remember, we're starting with what we know. Start with what you know. We're starting with the reactant or product that we know the mass and the RFM of, and that's with magnesium. So we're starting with magnesium. I need to convert this mass of magnesium into moles. How I do that is by using the equation N equals mass over RFM. And again, I'm just writing that underneath this part of the equation, and it'll just help me keep track. So the mass of magnesium is 4.8. Again, remember to check that that's in grams. And your RFM is 24. So I'm putting into my calculator 4.8 divided by 24. And make sure you have your calculator and do these along with me. That gives you 0.2 moles. And you can do just abbreviate that to MOL, 0.2 moles. So 4.8 grams of magnesium is equivalent to 0.2 moles. I can now bring that anywhere in my equation, absolutely anywhere. I can bring it to hydrochloric acid, to magnesium chloride, or to hydrogen, but I've got to be careful about my balancing number ratio. So I'm just going to quickly draw a box around my 0.2 moles because that's what I am moving. And I'm essentially just going to draw an arrow from where I'm bringing it from to where I'm going to. I need to bring it over to my magnesium chloride. But what I need to consider is my balancing number ratio. Now you'll notice in front of my magnesium, there's no balancing number. And that essentially means 1 mole of magnesium. In front of my magnesium chloride, again, there's no balancing number ratio. And again, that means that essentially it's giving me a ratio of 1 mole of magnesium chloride. So my ratio here is 1 to 1. And essentially what that means is that 1 mole of magnesium will give me 1 mole of magnesium chloride. So for every 1 mole of magnesium, I'm going to get 1 mole of magnesium chloride. Essentially, it's the same number of moles. What I'm really doing is I'm dividing by 1 and I'm timesing by 1. And you can see that that's just going to give me the same number. 0.2 moles divided by 1 times by 1 is obviously going to give me 0.2 moles. So the number of moles produced of magnesium chloride is 0.2 moles. So in this case, it's just worked out as the same, but that's because my ratio is 1 to 1. So that's step number 4 complete now. And step number 5 is then to convert your number of moles that you've brought over to mass using the equation mass equals N times RFM. Because look back to what I underlined in red. I've been asked to calculate the mass of magnesium chloride formed. So if you need to remind yourself at this part of the calculation, what actually am I being asked to do? What am I actually trying to work out here? You're trying to work out the mass of magnesium chloride. Now that I have the number of moles of magnesium chloride, I can convert that to the mass of magnesium chloride formed by using the equation mass equals N, the number of moles, multiplied by the RFM. The number of moles I've just worked out is 0.2. My RFM is 95. I put that into my calculator, 0.2 multiplied by 95. And that gets me a mass of 19 grams. Make sure you include your units. And remember, if you've used this equation properly, your units will always be in grams for the mass. So what I've been able to work out from this calculation is that if I react 4.8 grams of magnesium with hydrochloric acid and it reacts fully, then in theory, I should produce 19 grams of magnesium chloride. So there's a few steps in that, and it's just about making sure that you do each step each and every time. What I would suggest that you do now is pause the video, make sure that worked example is written in completely, making sure you write all of your balancing number ratio and everything, all your workings out in that. And then what I would suggest you do is try worked example 2. So worked example 2 should be exactly the same as worked example 1. You're given your mass of calcium carbonate and you're asked to calculate what mass of calcium oxide would be obtained. So there's nothing different in this example, and what I would challenge you to do at this stage is pause the video and try and work through steps 1 to 5. Calculate your mass of calcium oxide and then watch the video to make sure you're correct. If you're not feeling confident enough to do it by yourself at this stage, then I will take you through it now. Just watch the video, I'll take you through it. But maybe don't write it out yourself now, and then see if you can write in and do it yourself afterwards. So if you haven't already done so, go back, write in worked example 1, and then give worked example 2 a go if you feel up for it. Okay, let me take you through worked example 2 here. And if you're not confident what you're doing yet, that's absolutely fine. Just let me take you through it, but maybe not write it in at this stage. Let me take you through it and then see if you can do it for yourself afterwards. So we're being told that 5.0 grams of calcium carbonate is heated to constant mass. That just simply means that it reacts fully. Sometimes there's phrases like this in the questions and they don't overly matter in terms of our actual calculation. So 5.0 grams of calcium carbonate is heated to constant mass, in other words reacts fully. What mass of calcium oxide would be obtained? So let's think through our steps first of all, make sure we have all the information we need written down and underneath the equation. I always think that's the most helpful way to do these calculations. So we've got our equation here and we're going to work underneath it. So the first thing, step number 1 is write all the information you know underneath the equation. So what have I been given the mass of? Well, here's the mass here, 5.0 grams. That's the mass I've been given. And what's that the mass of? It's the mass of calcium carbonate. So I need to find calcium carbonate in my equation and I need to write this mass underneath it. So calcium carbonate is going to be CaCO3. So I'm going to write 5.0 grams underneath that. Second part of step 1 is to write a question mark underneath what I'm trying to work out. So let me go back to the question. It says what mass of calcium oxide would be obtained. So I want to ultimately work out the mass of calcium oxide. So I'm going to put a question mark underneath calcium oxide in my equation, which is CaO. So those are the two things I'm working with. I can essentially ignore carbon dioxide. It's not going to be part of this calculation. So I'm going to be using calcium carbonate and calcium oxide. So step number 2 then says write the RFM of the reactants or products that you will be using underneath the equation. So I'm going to use the RFM of calcium carbonate. So let me write the RFM of it underneath. So the RFM of calcium carbonate, I've been given that, is 100. I'm also going to need the RFM of calcium oxide, so let's write that in as well. Again, it will be given to you in the question. The RFM of calcium oxide is 56, and that means they're there when I need to use those equations later on in my calculation. We're on to step 3 now of our calculations, and that's essentially start your calculation with what you know. You've been given the mass of calcium carbonate, so that's where we can start because we can use our equation N equals mass over RFM. We can't start with calcium oxide because we don't know the mass of it. So we're going to start with calcium carbonate. So I'm going to use my equation N equals mass over RFM because I can't bring the mass of calcium carbonate over. I need to calculate the moles first. So N equals mass over RFM. The mass is 5. The RFM is 100. 5 divided by 100 is 0.05 moles. So 5 grams of calcium carbonate is equivalent to 0.05 moles. Step number 4 is to bring that then over to the reactant or product that you're trying to work out the mass of. And again, I need to check my balancing number ratio. So I'm bringing it over to calcium oxide here. So I'll draw my arrow first of all, and then I need to check my balancing number ratio. There's no number in front of calcium carbonate, so that's essentially a ratio of 1. And there's no number in front of my calcium oxide, so essentially that's a ratio of 1 as well. So my ratio here is 1 to 1. In other words, the same number of calcium oxide moles will be formed from the number of calcium carbonate moles. So 0.05 moles of calcium carbonate will form 0.05 moles of calcium oxide. If you want to do it fully, essentially you're dividing by your first number and multiplying by your second number, dividing by the number in front of what you're coming from and multiplying by the number in front of what you're going to. But 1 to 1 essentially means you're going to form the same number of moles to where you're going to bring it to. Okay, and then we're on to step number 5 now, and that's converting your number of moles to the mass using the equation mass equals N times by RFM. Because remember, what I'm being asked to calculate is the mass of calcium oxide that would be obtained. So let's have a think. What is N? N is our number of moles, which we know is going to be 0.05 moles of calcium oxide formed. We multiply by the RFM, which is 56. Put that into your calculator. 0.05 times 56 is equal to 2.8 grams. Again, remember to include your units at the end of your question. And if you've been using this equation properly, your mass should come out in grams. So hopefully you're starting to see that how you do these types of calculations, the steps that you follow are exactly the same each time. Your numbers will be different, your masses will be different, your RFMs will be different, and in some cases your balancing number ratios will be different, which we'll come on to an example of now. So hopefully after the first couple of examples you'll be confident in the method that we're using in these calculations. But those first 2 examples that we looked at both involved masses where the mass was in grams, and that's not going to be the case for these next few examples. And then also we saw 1 to 1 ratio in terms of our balancing number or our stoichiometric ratio. And that, again, that's not going to be the case in these examples. So the method is exactly the same. You follow the same method each and every time. But these are just going to have slightly more difficult units to work with and a slightly more tricky balancing number ratio as well. So let's read worked example 3. So it says, in the blast furnace, hematite, Fe2O3, is converted to iron. What mass of iron can be obtained from 16 tonnes of iron oxide? So let's follow exactly the same steps. So step number 1 is write the information that you've been given underneath the relevant part of the equation. So the mass I have been given is 16 tonnes, and that's of iron oxide being Fe2O3. So I could write underneath here 16 tonnes. But what I need to remember is that I can't use tons in my equation. The mass must be in grams. So how do we convert tons into grams? Well, there's a couple of ways you can do it. First of all, you can just simply times by 1,000,000. So that's 1 with 6 zeros afterwards. That's going to get you, obviously, 16 million grams. Or what you can do is think that there are 1,000 kilograms in a ton. So if you want to convert it to kilograms, you would times by 1,000, and that would be 16,000 kilograms. And then how do you convert from kilograms into grams? Again, you multiply by 1,000. That's adding on 3 more zeros, and so you would get 16 million grams. So either you can do it one step by multiplying by 1,000,000, or if you remember that it's 1,000 kilograms and that there's 1,000 grams in each of those kilograms. So I need to convert it to grams first of all, and I'm simply going to write that underneath the part of the equation as well. So I have 16 million grams of iron oxide. This is an industrial scale reaction, which is why the mass we've been given is so big. The second part of step 1 was to write a question mark underneath what we're trying to work out. In this case, we're asked what mass of iron can be obtained. What mass of iron can be obtained? So I need to find iron in my equation. Iron is Fe, and so I write a question mark underneath Fe. Step number 2 then was to write down the RFM of the things I'll be using. I'll only be using iron oxide and iron, so I only need to worry about their RFM. The RFM of iron oxide, Fe2O3, is given to me here as 160. Remember, always look for in the question for those RFM values. What's the RFM of iron? We can see it is 56. So write your RFMs underneath. Next, we're on to then step number 3, which is convert your known mass into moles. Essentially, I'm starting with the information I've been given. Start with what you know. I'm going to use the equation N equals mass over RFM because I want to convert the mass I've been given into the number of moles of iron oxide. So N, number of moles, is equal to mass over RFM. My mass is 16 million. And I divide that by the RFM, which is 160. Again, put that into your calculator, 16 million divided by 160, and that should give you 100,000 moles, MOL. So that's the number of moles that I'm going to be bringing to the other side of my equation. But I don't just bring it straight over. I need to consider my balancing number ratio. So I'm bringing it over to iron, but I need to consider my balancing number ratio. Here there's no number in front of my iron oxide, so essentially that's 1. But there's a 2 in front of my iron. So that means my ratio this time is 1 to 2. What that means is for every 1 mole of iron oxide, I'm going to produce 2 moles of iron. So if I have 100,000 moles of iron oxide, I'm actually going to produce 200,000 moles of iron, because remember, every 1 iron oxide gives me 2 irons. Or essentially, if you want to look at it numerically, I'm dividing by the number in front of what I'm coming from, which is 1, and I'm multiplying by the number in front of what I'm going to. So I'm dividing by 1 and timesing by 2. So 100,000 divided by 1 is 100,000, multiplied by 2 is 200,000 moles. So I'm actually producing 200,000 moles of iron. So be really careful. That's why our balancing number ratio is really important. Up to now we've only looked at examples where the ratio was 1 to 1, but here we can see the impact of that balancing number ratio. Once we've got our number of moles over with iron, then it's a case just of converting back to mass. How do I convert back to mass? Well, I use my equation. Mass equals N times RFM. The number of moles is 200,000 times by the RFM, which is 56. Put that into your calculator and you should get 11,200,000. What unit is that in? It's in grams. But you'll notice that's a very big number. And so we don't need to keep it that big. In fact, the question might ask you to give your answer in kilograms or in tons. How do we convert back to tons then? Well, if you look back up to the top of the question here, we converted tons into grams by multiplying by 1,000,000. So how we're going to convert back from grams into tons is we're going to divide by 1,000,000. So in this case, we're dividing by 1,000,000. If you want to write that in, you can. Divide by 1,000,000. Put that into your calculator. 11,200,000 grams divided by 1,000,000 is going to give you 11.2 tons. That just tidies your answer up a bit, and the exam question might actually ask you to give your answer in tons. So in this case, we had a couple of extra things to think about. First of all, converting our units into grams, but also our balancing number ratio was not just simply 1:1. And that meant when we got to step number 4 of transferring the number of moles across, we had to multiply the number of moles by 2 according to our balancing number ratio or our stoichiometric ratio. And that's just given to you in the note down here. So you can have a read at that note. It explains why we multiply by 2. So if you haven't already done so, write in the solution to worked example 3, and then what I would like you to do is have a go at worked example 4 by yourself. Try it, maybe do it on a spare piece of paper in case you get anything wrong, and then you can check the video, check that you've got the right answer, and then write that in so that your notes are complete. So if you need to, pause the video to write in worked example 3, and then give worked example 4 a go yourself before watching the video. Again, you just need to be careful about units and your balancing number ratio. So in this example, you're told that you have 27 kilograms of aluminium. So you're going to need to convert kilograms into grams, and you do that by multiplying by 1,000. So try worked example yourself first, pause the video, and then use the video to check your answer. So let's have a look at worked example 4 and check that you've got on okay with that. So we're told in question number 4 that 27 kilograms of aluminium were heated in a stream of oxygen until constant mass was achieved. Essentially that just means until all the aluminium had reacted. And it says determine the mass of aluminium oxide formed. So step 1 is write down the information we've been given. So the mass I've been given is 27 kilograms, and that's of aluminium. So aluminium is Al, so I write down 27 kilograms underneath, but we know that we need to convert that to grams. How do we convert it to grams? We times by 1,000. There's 1,000 grams in each kilogram. So that's 27,000 grams of aluminium that I have. So I'm going to write that underneath my equation as well. Okay, next part is to write a question mark underneath what I'm trying to calculate. It says determine the mass of aluminium oxide formed. So I'm going to put a question mark underneath Al2O3. Aluminium oxide is Al2O3. And also it's the mass of aluminium oxide formed, so I know it's going to be a product. Next step is to write down your RFM of the things we'll be using. We can forget about oxygen. It's not going to be involved in my calculation. So the RFM of aluminium, I've been given that, is 27. You could also just find that straight from the periodic table. And I'm going to need the RFM of the thing I'm trying to work out, which is aluminium oxide. And I'm told that the RFM of that is 102. Next step is step number 3. Start with what you know, and that is I know the mass of aluminium, so I start there and I convert that to moles. I convert that by using the equation N equals mass over RFM. The mass is 27,000 and the RFM is 27. So 27,000 divided by 27 is 1,000 moles. So that's the number that I'm going to be bringing over to my aluminium oxide, 1000 moles. So let's draw the arrow in first of all, from where I'm coming from to where I'm going to. And I need to look at my balancing number ratio, or my stoichiometric ratio. You can see here that the ratio is 4 to 2. So I'm going to write that on my arrow, 4 to 2. And you can do it that way. Essentially what you're doing is dividing by 4 and timesing by 2. You might want to use your calculator for that, just to be sure of that. Or what you can do is you can simplify that down. So a ratio of 4 to 2 is the same thing as saying a ratio of 2 to 1. Essentially, I've just divided both numbers by 2. So it's a bit like when we were doing our swap and drop with valencies. Can we simplify the ratio down? Is there a number I can divide both of those by? So 4 to 2 is the same thing as saying 2 to 1, but it's going to work the same way both times. Essentially what I'm doing is I'm dividing by the number in front of what I've come from and multiplying by the number of where I'm going to. So it's divided by 2 times by 1. So essentially overall what you're doing here is you're halving the number of moles. So be really careful with this, because you can see from my equation that for every 4 moles of aluminium that I have, I'm only producing 2 moles of aluminium oxide. So I'm actually producing half the moles of aluminium oxide as I had of aluminium. So just be careful you're doing it the right way around. This time I'm dividing by 4, multiplying by 2, or you can think of it as dividing by 2 times by 1. So essentially 1000 divided by 4 would be 250, multiplied by 2 is then 500. And again, put that into your calculator if you need. Just make sure that you make no mistakes with calculation errors. So I'm going to produce 500 moles of aluminium oxide. But my question didn't ask me for the number of moles of aluminium oxide formed, it asked for the mass of aluminium oxide formed. So I need to use my equation. Mass equals N times RFM. My number of moles is 500. My RFM is 102. That gives me a mass of 51,000. Let's think about our units. Remember, when we use this equation, gives our units in grams. And what I might want to do to tidy off that answer is to divide by 1000, since it's quite a large number. If I divide by 1000, that gives me my answer in kilograms, which is 51 kilograms. And again, the question in the exam might actually ask for you for the answer in kilograms. So you just divide by 1000. So 51,000 grams, divide by 1000, and that would get you 51 kilograms. So again, just be careful in this example with your units. You were given mass in kilograms, so you've got to convert that to grams first of all. And then just be careful with your balancing number ratio. Make sure you understand what it's really meaning. Thinking to yourself, am I getting bigger or am I getting smaller? Here I'm going 4 to 2. Which is getting smaller, so it's half the number of moles. So just think to yourself, does my answer actually make sense when you're transferring that number of moles? But essentially you're always dividing by the number in front of what you've just worked out and multiplying by the number in front of what you're about to work out. And the final example we're going to look at before you do some for yourself is worked example 5. And essentially this is just showing us that once you've worked out the number of moles of a reactant or a product, you can bring it anywhere in the equation. So in this example, we're actually going to be given the mass of a product, and we're going to be asked to calculate the mass of reactant needed to produce that amount of product. But you're doing the exact same thing. So it doesn't matter where we start, doesn't matter where we're going to, as long as we've converted to moles first, we can go anywhere in the equation. So let's read worked example 5. It says cells in our body use the breakdown of glucose as a major source of energy. Essentially this is representing the reaction of respiration. Glucose burns in an excess of oxygen to form carbon dioxide and water. Calculate the mass of glucose required to produce 432 grams of water. So again, our steps are no different. Step number 1, write the information that you know underneath the equation. So the mass I've been given in this example is 432 grams, and that represents the mass of water. So I'm going to write underneath my water, and water is H2O, that I have 432 grams of it. So this reaction is producing 432 grams of water, and it's in grams, so I don't need to convert it. Our units are fine. The second part of step 1 is to put a question mark underneath the thing that I'm trying to work out. So the question asks me to calculate the mass of glucose. The formula of glucose is C6H12O6. If you weren't sure of that, you'll know that it's a reactant because it's calculate the mass of glucose required to produce this amount of water, and you'll know that it's not O2. O2 is oxygen. So glucose is C6H12O6, so we put a question mark underneath there. Step 2 is write down the RFM of the things you will be using. So I'm going to be using glucose and water. So those are the only RFMs I need to write down. So the RFM of glucose you've been given as 180, and the RFM of water is 18. Step number 3 then is to convert your known mass into moles. And here's where this question will start to look a little different to what we've done before, because this time our known mass is actually a product. We know the mass of our product, and we're trying to work out the mass of reactant needed to produce that amount of product, to produce that amount of water. So I'm starting here. I start with what I know. I start with the mass that I know, because I couldn't calculate the mass or the number of moles of glucose at this stage because I don't have a mass. So I'm using my equation N equals mass over RFM to calculate the number of moles of water that I want to produce. So the mass is 432, the RFM is 18. Put that into your calculator and you get 24 moles of water. So this reaction is producing 24 moles of water, and I want to work out what mass of glucose is needed to produce 24 moles of water. So I need to bring this number of moles over to my glucose, but I'm going to have to think of my ratio. Let's think about the direction we're going here. We're going from water to glucose. So I'm going from water, which has a balancing number of 6, to glucose, which has a balancing number of 1 essentially. So my ratio here is 6 to 1 because I'm going from water to glucose. I'm going from right to left in this case. So I'm going from a ratio of 6 to a ratio of 1, and that means I need to divide by 6 and times by 1. So just think really carefully about the direction you're going. You're going from 6 moles of water to 1 mole of glucose. So essentially I'm dividing by 6 in this case. So 24 divided by 6 and times by 1, if you want to think of it that way, is going to give me 4 moles of glucose. So I need 4 moles of glucose to produce 24 moles of water. But the question didn't ask me for the number of moles of glucose, it asked me for the mass of glucose. So I need to use my equation, mass equals N times RFM, to work out the mass of glucose required. The number of moles required is 4. The RFM is 180. So 4 times 180, put that into your calculator, and you should get that your mass is 720 grams of glucose. So we've answered our question now. Calculate the mass of glucose required to produce 432 grams of water. Well, I need 720 grams of glucose to produce that mass of water. So what we're saying from this example is that whatever mass you're given, you can go any direction in this equation. The mass that you're given, you can convert to moles, and then use your balancing number ratio to bring that to the reactant or product that you're trying to work out the mass of. Just be really careful about the direction of your ratio, thinking I'm going from whatever I've just worked out to what I need to work out. So in this case it was 6 to 1. Dividing by 6, timesing by 1. So that's your worked examples finished. Make sure those are all written in and they're all written in accurately so that you have accurate worked examples in your notes. I'm going to now explain what I want you to do next. So over on page 20 and 21, you have a further 6 examples of these. And what I would like you to do is to complete these in your blue book. So you're completing all the questions in the next 2 pages, page 20 and 21. There's 6 questions in total in your blue book. There's a couple of things I want you to make sure that you do. First of all, I want you to make sure you show all your working out. So what that will involve is rewriting the balance symbol equation that you've been given in the question. I would try and stretch that out across the width of your page, but make sure you do fit it in one line so that you don't have some of your products on the left hand side if you're taking a new line, for example. So rewrite the equation and work underneath. You'll always be given the balance symbol equation. You don't need to worry about balancing it. But you do need to rewrite that so that you can work underneath, as we have done in our worked examples. So show all your working out, rewrite the equation and work underneath. I'll show you briefly how I want you to set out question 1 before you start. The next thing I want you to make sure you do is check your final answer for units, so include units in your final answer. Generally those units will be grams, because you're asked in each of these types of calculations to calculate the mass of such and such produced, or calculate the mass required to produce this amount. So generally your units will be grams, but if your final answer is a really big value, remember you can convert it to kilograms or tons if it gives you a tidier answer. So remember also to check the values given to you in the question that they are in grams. So you need to check that first. And then finally, what I want you to do is ask yourself, does your answer match? So what you'll notice in that each question, I have given you the final answer in brackets and in bold. So I'm highlighting the answers here. So that should be your final answer. If that's not what you get, you've done something wrong. So you need to go back and identify, perhaps you haven't converted to grams, perhaps you've used the wrong RFM, perhaps you haven't used your balancing number ratio correctly. And if you're struggling with these, go back and watch the worked examples again. All of these will be done in exactly the same way as the worked examples, but just with different formulas and different numbers essentially. So you're using exactly the same method. Go back to page 16 for your step-by-step method if you need. If your answer doesn't match, you've done something wrong and you need to try and correct that. Try and work towards getting the correct answer. And if you're struggling, you've done it a couple of times but you're not getting your answer to match, then email me and let me know. I can help you with particular examples, but try and find the problem yourself before coming to me. And again, I've given you those answers so that you can check as you go along, am I on the right track? Am I doing these correctly? If you've got the right answer, the chances are you've done this correctly, you've followed the right method. But if you're not getting that answer, then you've done something wrong. I haven't given you the answers to just so that you can just write those down. You need to do the working out yourself, show your answer, and make sure that you can do it yourself. It's just there for you to check if you're doing it correctly or not. So I want you to have a go at these 6 questions now, and then I will be expecting you to send me the solutions, send me a picture of all of your working out, so make sure all of your working out is shown carefully. I'm just going to show you briefly how to set out question 1. I'm just going to start it off for you, I'm not going to do the whole thing, and then you can have a go at these. So very briefly, just to show you how to set these off and to set them out correctly and how we've done them in our worked examples to help you out a little bit. So question number 1 says calcium carbonate reacts with hydrochloric acid to form calcium chloride, water and carbon dioxide according to the following balance symbol equation. Then part A asks you to calculate the mass of calcium chloride produced when 25 grams of calcium carbonate completely reacts with excess hydrochloric acid. So what I would be expecting in your blue book is for you to write 1A. Write out your equation first of all, so always write out your equation first. Try and spread this across your page, but make sure you fit it in one line. So CaCO3 plus 2HCl, giving you CaCl2 plus H2O plus CO2. Make sure that you include all your balancing numbers. If you don't include the balancing numbers, then you will get these calculations wrong. So remember, our very first step is to write what we know underneath the equation. So I've been given a mass of 25 grams. What's that the mass of? It's of calcium carbonate. So I write 25 grams underneath my calcium carbonate. It's in grams, so that's fine. I don't need to convert that mass. Next thing is to write a question mark underneath the mass that I'm trying to calculate. It says calculate the mass of calcium chloride produced. So it's produced there. I know it's going to be a product. Calcium chloride is going to be CaCl2. So put a question mark underneath that. Your next stage then is to write down the RFMs of what you're going to be using. So I'm going to be using the RFM of calcium carbonate and of calcium chloride. I can essentially ignore the rest. So the RFM of calcium carbonate is 100. Make sure you pick the right RFM, and sometimes that can be a mistake as well that people make. And the RFM of calcium chloride is 111. And then from here, you just set that out as we have done before. You'll be starting with your calcium carbonate, calculate your number of moles by using your equation, N equals mass over RFM. Calculate your number of moles and then bring that over to your calcium chloride, checking your balancing number ratio. I'm not going to do that all for you. You've plenty of worked examples to work from, but just showing you how to set that out. So set each and every one of them out like this. Writing out your equation, writing the information you know underneath, then carrying out your calculation and maybe highlighting your final answer or putting a box around it so it's easy to see.